So we're going to start today doing confidence intervals like we ended yesterday doing. So we're doing confidence intervals like we ended up doing yesterday. Okay, so there's two kinds of thread are being compared for strength. 50 pieces of each type of thread are tested under similar conditions, and the sample data is given in the following table. We want to construct a 98% confidence interval for the difference of the population means. Now, the first thing that we have to do is get our degrees of freedom. They give us everything else. They give us N1, if my pen will write. They give us N1, N2, X bar 1, X bar 2, S1, and S2. We know all of that. So it's going to kind of look hodgepodge up here on the screen because I'm going to have to use pretty much the whole screen. If I go to the next slide, then boom, there's all the calculations, and I don't want us to do that. Let's develop them. Okay, so for V1, let's do the V's over here. So for V1, remember it's S1 squared, so 5.62 squared over N1, so over 50. 5.62 squared divided by 50 is what to 3 decimal places? That's right, 0.632. So there's V1. V2, that means 6.31 squared divided by N2, which is also 50. So if we do that one to 3 decimal places, 0.796. We've got our V's, now let's get our degrees of freedom. So I'm going to write the formula over here so we can see where to plug everything in. This is what I meant by it's going to be kind of hodgepodge, just kind of all over. Okay, let's plug everything in that we know. So V1 we said 0.632 plus 796 squared over 0.632 squared. Well, for the bottom, oh, I left something out. It should be in my N1 minus 1 and N2 minus 1. Whoopsies. 50 minus 1 is 49. Just ignore this one. Plus, let's see, 0.796 squared over 49 again because they have the same sample size. What does that get us for degrees of freedom?
0.076.
0.7. That sounds way small. And those of y'all that are verbal, I know I haven't really emphasized this much, but anytime y'all want to grab a calculator and do calculations and put your answer in chat, see if you can beat those in class. Go for it. Yep, Michaela got it. 96. The degrees of freedom here, that the full number is, where did I put it? 96.7. Oh, go back. Go back. I got 96.7, but since we have to truncate, degree of freedom would just be 96. Okay, now we need to figure out our critical value for this hypothesis test. So we want a 98% confidence interval with 96 degrees of freedom. If we look at our t-table, will there be a row for 96? No. What's the closest row to it? 100. I don't think there's a row for 95. It's 100. So we could use that estimate, and we would get what? So if I use 100 degrees of freedom for a 98% confidence interval, what would I get for my test statistic? 2 point. Well, she. What would it be? 2 point. I'm going to show you how to put it in the calculator. I'm wanting us right now to look at our t-table at 100 degrees of freedom.
2.364.
Yep, 2.364. So let's write this value down. This is what we're going to use to calculate this example. That's what the PowerPoint uses, so that's what we'll use. But I want to show y'all something that you can do in your calculator. So let me clear out my steps here. What we can do, y'all remember how we got to that TCDF? Where we did second and vars, and there's that TCDF. Well, I don't want the CDF. I want the inverse T. Now, a 98% confidence interval, let's take a step back and think back to when we were doing confidence intervals for dual credit. If we're 98% confident for our interval, how much is in each tail of the interval? What percent is left for each tail? 1%. So when it says area for inverse T, we wouldn't want to put 0.01, we'd want to put 0.99. What we're doing here is we're giving it the area and the degrees of freedom, which we said was 96. And then it's going to tell us what critical value we would have. So inverse t, 0.99 and 96 are our parameters for this function.
Wait, how do we know the area?
Well, we have a 98% confidence interval, right? How much does that leave us for each tail to be left? If 98% is in the middle, what's on each edge? 1%. So what I'm doing is I'm finding where does that 1%, where's that 1% at on the upper end? That's why we did 0.99, because that'll get us the point to where, okay, starting here starts my 1%. Does that make sense? That's our actual, like, if you want to be technical, here's your critical value. That's the actual critical value. How close were we in our table? Pretty close, weren't we? So that's why it's like, let's just use the table. 100 is pretty close to 96. At this point, we're within, what, 2 thousandths? I mean, just for laughing measure, let's put in the one we were going to use. That's all we're off on. We're within 2 thousandths of the actual value. But now you know how to do that with the calculator for AP. That's really the whole reason I wanted to show this, was for y'all for the homework.
Degrees of freedom doesn't make that much of a difference. Like if you go down 25 degrees of freedom, it's only like 0.01 off. Which I mean, I guess that's a fairly big difference, but
Yeah.
if you use 75 instead of 96, it's only 0.01 off.
Yeah. Well, look how big our sample size is. Remember what we said, once you get above 30, things really start getting pretty close to being normal. So that's why. That is why. Okay. Anyways. No, come back to me.
Wait, is what homework due?
What was that?
Is homework due today or?
For the end of 11.1, yes. Okay, so, and all this paragraph really does is describe what we just did. So if you're trying to feverishly copy it, don't worry about it. It's just describing what we just did. Our actual interval, I don't want that up there. I want us to find it. Thank you. So for the actual interval itself, we remember our formula. X1 bar minus X2 bar plus or minus T crit, which, just to recall, we said T crit is equal to, what did we say it was? 2.364. And then we have the square root of S1 squared over N1 plus S2 squared over N2. Yes.
If you're calculating, if you're doing the equation for degrees of freedom, both data sets have the same number, you would still need to do
Like both data sets
the
have,
same sample size.
yes,
You still need to do it.
yep. That's what we actually had on this example, if we go back.
Oh, yeah,
Going the wrong way. See, they both have 50 degrees of freedom. I mean, even if we did n minus 1 times 2, that'd be 98, so we'd still be off. That make sense? Okay, so let's plug in what we know. Now, my values aren't up on the screen anymore, but you have the table right up above where you're writing. So if we plug in x bar 1, that's going to be 78.3 minus 87.2 plus or minus. T critical was 2.364 times the square root of 5.62 squared over 50 plus 6.31 squared over 50. Okay, so if I do the left side first, what should I get? So I want to do each one of these. That's okay. We're still on the first example.
Really?
So if I do the first group, I should get negative 8.9 plus or minus. And then our standard error over here would be what? The 2 decimal places. 2.82, that's right. So our interval itself would be, let's see, negative 8.9 minus 2.82 would be negative 11.72. And then negative 8.9 plus 2.82. Yep. There's our interval. So I'm actually about to erase the ink on here since this is everything we just calculated. That way you can see the conclusion. So the 98% confidence interval estimate for the difference of the means of tensile strength is negative 11.72 to negative 6.08. Okay, questions on this example? Okay, let's move on to the next one then. Still writing? Okay.
This is the same kind of exam? Alright.
And both of these aren't really going to be tested for y'all. I mean, it's a good refresher to remember how to do confidence intervals, but they won't be on the test 4.
I got you. What about this 8.3? When is this gonna be due?
Monday.
Monday?
Yeah.
Yes, sir.
And I haven't told anyone this in this class for dual credit, I don't think. The assignment that I have due Friday, it's what I'm going to call a soft Friday. Meaning it can be done Saturday, it can be done Sunday.
All right. Thank you very much.
Just have it done before you come back Monday, please.
Yes, sir.
So 8.2, yes, I'm going to leave it in Blackboard as due Friday. So even if you do it Saturday or Sunday, Blackboard's going to tell me it's late, but I'm not going to count it late.
Yes, sir. Thank you.
Then 8.3, honestly, with grades being pulled tomorrow, I probably won't get 8.3 put in Blackboard until Saturday.
Real quick question, the core assessment, how does that work necessarily? Like, I know it was talking something about like 20 points or something like that. Like,
How does it factor into your grade?
just like, is it 20 points of our grade?
No,
Okay.
it's 3% roughly of your overall grade.
Okay. I was just checking because I saw that 20 points and it confused me a little bit.
Yeah, it's 3. Because like total, if you consider that each test is 100 points, homework's 100 points, and then this assessment 20 points total in the class, you can get 620 points. So if you do 20 divided by 620, that comes out to like 3.23%.
Yes, sir. You're gonna get 8.1 and 8.2 in the grade book though before Friday, right?
Well, 8.2 I won't because it's not due till Sunday. The core assessment and 8.1, I'll get all the way through 8.1 in the grade book by Friday.
All right.
By tomorrow.
Yes, sir.
That's what I get to go home and do tonight, grade. Okay, next example. We gotta get moving. A student recorded the mileage he obtained while commuting to school in his car. He kept track of the mileage for 12 different tankfuls of fuel involving gasoline of 2 different octane ratings. Compute the 95% confidence interval for the difference of mean mileages. And then there's his data. So just to keep things moving quick, I want let's see, these first 3. So Riley, KJ's, and Brandon's row.
Okay.
Somebody in y'all's row, I want y'all to do the one variable stats for 87 octane gas. So put those in L1, get me the one variable stats. Everyone else, I want y'all to do the 90 octane. And then virtual, you can pick one. The one variable stats for the Inspire, I want to say you from the scratch pad, you
Menu, stats, and then one variable stats.
from the scratch pad or from a spreadsheet?
You have to go to a spreadsheet. You can't do it on a spreadsheet.
Okay, so you have to create like a spreadsheet and enter them in, and then hit menu, stats, and one variable stats. Does that help, Michaela? No problem. Okay, so anyone got the stats for 87 octane? We'll come back to that one. What about 90 octane? 30.73 for the mean. Okay, what about the standard deviation?
1.39.
Yep. And the sample size? Okay. 87 octane. Yep. Standard deviation. Yep. And sample size. Okay, so those are our one variable stats. I put them up here for reference, that way we can still see them, so they're not totally gone. Okay, we need to get the critical value. So how many degrees of freedom? Oh wait, we gotta calculate it. Duh. We gotta calculate it. I'm thinking ahead to 11.2. That's when it gets easy for degrees of freedom. Okay, so we gotta do all the lovely V's here. So V1, 1.228 squared over 6. I'm gonna save you all these steps. Say 25.12. For V2, 1.392 squared divided by 6. Three, two, three. Let's say 3231. And then we have our degree of freedom formula. So V1 0.2512 plus 0.3231 squared over 0.2512 squared divided by, let's see, our sample size is 6, so I have to do 6 minus 1, which gets me 5. So I want you to finish this calculation right quick while I grab this.
What's your results, man?
Sit down. Okay, so let's see here. Let's say the 5 goes here. So what did you get for standard deviation? Sorry, degree of freedom. What did we get for this formula? Nine, that's right. So degrees of freedom are 9. It's really like 9.8, which goes down to 9. So this one is small enough that it's in our table. We need a 95% confidence interval. So we can do, look for 0.95 confidence, 9 degrees of freedom, and what do we get for our critical value? 2.262. Okay, so from there, let's calculate our interval. I'm not going to write the formula out this time. Typically you would, just so you know what to plug in and where. But I'm just going to jump into it. So 28.45 minus 30.73 plus or minus 2.262 times the square root of 1.228 squared over 6 plus 1.392 squared over 6. So now you have found our difference, combine that together, which would be negative 2.28 plus or minus. And then let's find our standard error. Well, you should get 1.71 for that one. Okay, so that means our interval is negative 3.99 to negative 0.57. Questions on this one? Okay. Nope, I guess we haven't stated our conclusion yet, so let's. So the 95% confidence interval for the true difference of mean mileages is negative 3.99 to negative 0.57. Anyone still trying to write that? Okay. Okay. So let's look at the pooled t-test. That's page 9. So we use the pooled t-test when the variances of the two populations are equal. This combines information from both of the samples to create a pooled estimate of the common variance. Notice, I'm not saying we're putting all the data in together. We're only doing this for the variance. We'll still have two separate means. We're just creating a common variance. The only problem with this is it's not widely used. It's used sometimes, but it's not widely used because it's really sensitive to any departure from the equal variance assumption. So for dual credit on your 8.2 assignment, it will actually say assume variances are equal. Assume variances are not equal. If it says they're equal, then we use a pooled t-test. If they're not equal, we can't. We use the one we've been doing the whole section. So when the population variances are equal, the pooled t procedure is actually better at detecting deviations from H naught than if we were to keep them into two separate samples. However, as I mentioned, if they're not equal, p-values computed using the pooled t procedure can be far from the actual p-value if the population variances are not equal. So it's a really good estimate if they're equal. It's terrible if they're not. Okay, so these next formulas are more for dual credit, not AP. So you may, on the blank area on page 9, you may want to write these down. Either that or have your formula chart out and make note of where they are. So for degrees of freedom, if they're equal, like we talked about, your degrees of freedom would be N1 plus N2 minus 2, if they're equal. If they're not, you essentially pick the smaller degree of freedom. Pick smaller degree of freedom. So you find the degree of freedom for each sample and then just take the smaller one. Now, if they are equal, so if this first one holds, then you can calculate S. That's going to be our pooled standard deviation. And then this S that you calculate is what would be used when doing a pooled t-test. Y'all don't need those. I mean, if you want to know them and you just a reference and you can say you know them, you can write them down, but y'all don't need them.
Which ones?
I was talking to AP. These that I'm saying y'all do need.
You hold the standard deviation and fortitude test. Those aren't needed by us.
They are needed by y'all.
Oh.
They're not needed by AP. AP just needs to know this method exists. Y'all have to actually be able to use the method. And it's really, there's only just one extra step. That's really the only thing that's different here. We still use S1, N1, S2, N2 in some degree. We just have to do an extra step with them. So.
Yeah, can you go back real quick?
Oh, I didn't mean to do that. Sorry.
That's all good.
I didn't mean to do that. And then I included that note on the bottom of the slide because y'all need to start using your formula chart now. Don't wait until the day before the test to start trying to get familiar with it. Start learning how to use it now, so then on the test, it's just second nature. So once I get through writing this slide, I want to talk about y'all's formula chart right quick. Anyone still writing?
Yeah, I mean, my bad.
Thank you. I scanned all the way through through Unit 9.
Oh,
I should be good for time for a while. Thank you.
welcome.
All right.
Got it.
Yes, sir.
Okay, so on y'all's formula chart, I briefly hit on this yesterday. But on y'all's formula chart, dual credit. The middle, kind of like the middle row, if you will, that's for section 8.1. So if you haven't started on the homework due tonight, this is your method here. On 8.2, these bottom two are your method. This top row is for pool. So that's the special case we just talked about. Now don't write this on your chart unless you want to be prepared to erase it on test day. The bottom row is like the one we've been using all along. And notice it even tells you which degrees of freedom to use. So you don't have to necessarily memorize it. You just have to know where to look on the chart for your situation. That's on theirs. That's on their formula chart. Yep.
What's on our formula chart?
Everything on that screen, all the formulas on that screen.
I know.
We are good.
It's just like 2 full tests, or 2 field tests, blah, 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 2 samples, stuff like that.
We
And then just finish the
basic
formula.
equations We learned, you get the basic equations we learned the first couple of units. Like one from this, and then the 2 table ones you get.
Our formulas are really confusing.
Oh, yeah.
Right.
Yeah. I guess you can say that's one of the perks of dual credit. Okay, so middle one is 8.1, bottom 2 are 8.2. What we're about to start, for y'all's 8.3 homework, that's going to be this one right here. That would be y'all's 8.3, which is section 11.2. And then what do y'all think the top row would be?
7.1.
7's on the opposite side.
9.1.
8.4. So that way, start using them now on the homework. That way, yeah.
But we can't put that on the formula chart.
No, can't write it on there.
Dang.
Unless you either want to write it and then have to erase it on test day, or not use the formula chart. Yes.
What is 8.2 and 8.3?
8.2 is due no later than, it says Friday, but it's due no later than Sunday night. 8.3 is due Monday night. Okay, section 11.2. We gotta get rolling. This is where we should have started today. So we're going to kind of set the stage with an example. We're going to look at difference in means with paired samples this time. So let's just set the stage. This isn't in your notes. Just kind of go along with the example. Let's suppose an investigator wants to determine if regular aerobic exercise improves blood pressure. A random sample of people who jog regularly and a second random sample of people who do not exercise regularly are selected independently of one another. Yes.
You said just go with this? All right,
Yeah, we're just setting the stage for what is on your notes.
Yeah.
So based on this example, can we conclude that the difference in average blood pressure is due to jogging? What do y'all think? If one group jogs and the other group doesn't, at the end of the study, can we say one thing or another about, oh, blood pressure is decreased by jogging? Or does a person's blood pressure depend on more than just whether they jog or not? Yeah, it depends on more. What about other factors like weight? So one way to avoid this difficulty of extra factors being involved is to assign one of the pairs to jogging and the other in the pair to no exercise. So we would pair them by weight, and then one jogs, the other does not. Then you can actually tell a difference. That's what this section is going to cover. So let's kind of do a summary of the method, and then once we summarize the method, we're going to jump into calculations. So the null hypothesis is that mu G is, for AP, it's just mu D equals the hypothesized value. Remember, dual credit, you can have equals, you can have less than or equal to, greater than or equal to, as long as there's an equal to in there.
This is what we're putting in right now.
Now, what is mu D? Mu D is the mean of the differences in the paired observations. The hypothesized value is usually 0, meaning that our hypothesis is that there's no difference. So there's no difference in whether you jog or not on blood pressure. Along with that little example. Okay, for the test statistic, now we're kind of simplifying it. We got complicated. Now we're going to simplify it a bit. So our test statistic is that t equals x bar d, where x bar d is the mean of our differences, sample mean of the differences, minus the hypothesized value, divided by the standard deviation of those differences over the square root of n. Now, on like the dual credit assignments, the only difference really with this whole section is that y'all use, and on the formula chart, it uses D bar instead of X bar D.
All right.
So right here, the only real difference is it uses D bar instead of the X bar D. Yes.
The second blank it has the hypothesized value is usually blank. What was that?
0.
Gotcha.
What were you saying, KJ?
No, it's time.
Okay, our alternative hypotheses. So they're really just like the others. You can be greater than, which would be a right-tailed test. Where's my pen? There it is. This is going to be right-tailed. We can be less than, which would be left-tailed. Or we could be not equal to, two-tailed. I mean, the hypotheses really, alternative hypothesis, that's really kind of fixed. So it's going to be right-tailed, left-tailed, or two-tailed, no matter what kind of hypothesis test you're doing. Okay, so let's look at our assumptions then. First assumption, the samples must be paired. The samples must be paired. Second assumption, the n sample differences can be viewed as a random sample. from a population of differences. And then the third is that the number of sample differences is large, generally 30 or more, like we've always said, or the population distribution of differences is at least approximately normal. Okay, so let's look at some examples. Is the following an example of a paired sample? An engineering association wants to see if there's a difference in the mean annual salary for electrical and chemical engineers. A random sample of electrical engineers is surveyed about their annual income. Another random sample of chemical engineers is surveyed about their annual income. So they survey electrical, then they turn around and survey chemical. Are these samples paired? No, they're not. There is no pairing of individuals here, which means you have independent samples. Okay, what about this next one? A pharmaceutical company wants to test its new weight loss drug. Before giving the drug to volunteers, company researchers weigh each person, and then after a month of using the drug, each person's weight is measured again. Is that a paired sample? Actually, this one would be paired. Because you have two observations on each person. They're going to weigh them before they give them the drug, and then weigh them after a month of using it. So yes, this is a paired sample.
So what are the pairs of this?
The pairs, that it would be the one person's weight before and after. So what they would probably do is they would probably take the after weight. Sorry, let me erase it. They'd probably do something like before minus after, and then your variable would be the weight loss. So this is one data collection. This is another data collection. So we still have two samples here, but it's from the same person. Does that make sense?
Yeah.
Okay, so anyone in here know how to play chess? I kind of remember how to play. I haven't played in forever. What's
I haven't
that?
played in a long time, but
Beat all your checkers.
I don't like
I haven't played since probably elementary school.
Yeah, that's. I can't remember the last time I played. I used to have an uncle that like every time he came into town, he'd want to play me in chess.
Me and my brother used to be really competitive and we'd compete like once a week. So you could see who beat the other.
In eighth grade, I did like the UIO competition in chess.
Oh, cool. There's a lot of mathematics behind chess. Anyways, so there's also been a lot of studies done on chess because it's been theorized that playing chess actually helps improve your memory, improve your IQ, anything to do with the brain. There's been studies on can chess improve that functionality of your brain. So anyways, in this particular study, they took students who had not played chess and had them play chess daily for 9 months. Each student took a memory test before starting, and then at the end of the 9-month program, they took another memory test. They asked us to determine if there is statistical evidence that playing chess improves memory. So the first thing we need to do is find the differences. And to do that, even though this to me is totally backwards, we're going to do pre-test minus post-test. Completely backwards, but I didn't write the example. So when we do that, we're essentially having to go through each observation here and subtracting them. So 510 minus 850 gets us negative 340. 610 minus 790 gets us negative 180. 640 minus 850 gets us negative 210. And we just keep going through and doing that for every sample here. I'm going to save us time and say that's what you'll get and just put the row up there. What's that?
Homework tonight's gonna be pretty bad. You have to subtract all of them.
Okay, so now let's state our hypotheses. Let's think about this for a second though. If memory improves based on how we calculated this, remember we did pre minus post. If memory improves, should our number be positive or negative? Negative. The pre should be lower than the post. So that's our claim. Will this be the null or the alternative? This is alternative. I'm going the wrong way. That's our alternative. Mu d, the mean of the differences, is less than 0. That means the null is the mean is equal to 0 if you're AP. If you're dual credit, it would be greater than or equal to 0. Now, if we had done it the way I think we should have, let me erase this ink. Where's mine? if we would have done it the way I think we should have, and subtracted post minus pre, then the alternative would be greater than right here. But we didn't. So.
Is that one on page 9, is that 0 on the number covered up?
Yeah. Okay, let's check our assumptions. So that's the next thing we've got to verify. Now on this one, it doesn't state in the problem that it's a random sample. However, the investigator believed that it was reasonable to view the 12 sample difference as such. So it doesn't come right out and say it's a random sample, but we can view it as such. Our other assumption, what else do we have to check for? To see if it is normal. So if we do a box plot of the data, we'll see that the box plot's approximately normal. Or symmetric, sorry, it's approximately symmetric with no outliers, so normality is plausible.
Are we gonna have to write our assumptions down with this, or is it just the interpretation?
I think the main thing you have to worry about is the interpretation. Again, like I said, though, you will still need to know the assumptions, though.
Yes, sir.
Oh, you have staples? I kind of got used to the shoulder homework, didn't you?
Yeah, that's not, four problems couldn't be bad. And there weren't even parts to it. It was just like the problems are like half a page.
Yep. When I took college math classes, that was actually the norm. Half a page to a whole page problem.
That hook come to 0.
Yeah.
Yeah. Or 1 or something like that. Stick with it. Okay, so let's keep moving. Now we've got to compute the test statistic and p-value. To do that, though, we need to get our sample statistics. So I hope by now y'all know how to put them into one variable stats. Since we are running low on time, and I want to get through this example, I'll give them to you. So x bar d would be negative 144.6. SD 109.8. No, 0.7, sorry. 0.7, come on. 0.74. Really? And then how many samples do I have? Looks like I have 12.
Why is it D?
Well, that's what D.
Why is it like X bar D, S, D?
Because this is the mean of the differences. That's why y'all's uses like D bar
Yes, sir.
to show mean of differences. Okay, so let's compute the test statistic. That's going to be, I don't want to go that far. So T equals negative 144.6 minus, well, our hypothesized value is 0 over 109.74 divided by the square root of 12. Again, saving all the calculations. This would be negative 4.56. Now, for dual credit, y'all use the critical value rejection regions, right? Where you have to find the critical value and then see if it falls within the rejection region. That's how y'all would proceed with this problem. We're going to keep doing like what AP's done and use the use the p-value method. So for this one, what kind of test do I have? If it's less than, that's a left-tailed test. So for the p-value, I would need to find the probability that t is less than negative 4.56. How many degrees of freedom do I have? Oh, we're back to the old-fashioned n minus 1. So n minus 1 is 11. So if we did this using TCDF in the calculator, our lower bound would be negative 999. Upper bound is our test statistic, and then we've got 11 degrees of freedom. So this is in the TI-84 right here. And it would give us our answer in scientific notation, like 4.0 something E negative 4. If I were to write that in just standard form, this would be the p-value, which is pretty much what? 0. So p-value is pretty much 0. What alpha did they ask us to use in the problem? 0.05. So which one's smaller? P-value smaller, so what would we do? We reject, that's right. So I'm going to clear the ink off. See the calculation?
right, thank you.
So that way we can see the conclusion. I'm going to clear the ink. Since p-value is less than alpha, we reject H naught. So there is convincing evidence to suggest that the mean memory score after chest training is higher than the mean memory score before training. Which, remember, that's our claim. So if you wanted to write this the dual credit way, you could say there is sufficient evidence to support the claim. And we're not going to get as far as I wanted, but we're going to get close. We have to. We're actually not even going to get to where we got third period. We're going to be one example shy. Okay, let's go on and get the properties out of the way for the paired T confidence intervals. So when we have the samples being paired, the in-sample differences can be viewed as a random sample from a population of differences. And the number of sample differences is large or approximately normal. When all that occurs, then we can use the paired T interval for the differences. Again, this, remember, is just T crit. So AP, you may want to make sure you at least get this formula down because you'll probably have to do some confidence intervals. Where our degree of freedom is n-1. So I'll give y'all a little more time to write this down. I'm going to try, we've got 3 or 4 minutes, so I'm going to try to run through this next example as quick as we can, just so you see a confidence interval. It'll be in the video if you want to go back and watch it later, since I'm still recording. They want us to compute a 90% confidence interval for the mean difference in memory scores before chest training and the mean. Basically, it's our chest example again, but we're doing a 90% confidence interval. So to remind us of our sample statistics, X D bar, we said was negative 144.6. SD was 109.74. N was 12. Degree of freedom was 11. If we were to look up our T critical value, we're doing a 90% confidence interval with 11 degrees of freedom. That would get you a critical value of 1.796. So at this point, we can plug everything in. Negative 144.6 plus or minus 1.796 times 109.74 over the square root of 12. That's going to be negative 144.6 plus or minus 56.896, which gives us a confidence interval to 2 decimal places, a negative 201 point, let's do 1 decimal place, 201.5 to negative 87.7. There's your 90% confidence interval. So I'm going to erase the ink, that way you can really get a clear shot at it. So we're 90% confident that the true mean difference in memory scores is between negative 201.5 and negative 87.69. So we actually did get where I needed. It just took us literally until the bell.